Hello everyone, welcome to this video. In this video we'll be exploring examples, right? We'll be discussing about a question, a mapping such that we can see the application of properties of homomorphism, right? This is our aim. So here let's start by taking first of all defining a mapping phi from C star to C star. You know what is C star? It is a group of complex numbers where 0 is eliminated from the group and the operation is multiplication, right? The mapping is defined like this: phi of x is equals to x raised to power 4. Then we say phi is a homomorphism. How? You can clearly see if you take any two elements x and y, right, from C star, then what would be phi of x and y? It would be, by the definition, x and y raised to power 4. So you can separate out the powers. You can write it like this: x raised to power 4 and y raised to power 4. And what is x raised to power 4? It is phi of x, and y raised to power 4, it is y of phi of y. Correct? Okay, now once we know it is a homomorphism, we are able to apply the properties of homomorphism onto it. So let's see which all properties work here, and using the properties, what all information can we access from it, right? So first of all, let's see what is the kernel of this mapping. You know, by definition, kernel would contain all the elements x from C star such that when you apply this mapping phi onto x, you get the identity in C star, which is 1, correct? So by the definition of phi of x, you know, it is equal to x raised to power 4. So you are looking for all those elements x such that x raised to power 4 is equal to 1. Now, what all numbers will you get when you solve this equation, x raised to power 4? So here you see 1 raised to power 4 is also 1, minus 1 raised to power 4 is also 1, iota raised to power 4 is also 1, and minus iota raised to power 4 is also 1. Hence you have all these 4 as the answer to this equation. Hence they are the elements of your kernel. So you see, because there are 4 elements present, hence the order of the kernel is 4, correct? This is one thing. Another thing, we can see clearly say that because the kernel contains 4 elements within it, therefore this mapping is 4 to 1 mapping. So that means for every element, so suppose this is your G bar, this is your G, right? What is G here? It is C star and it is also C star. It is given to us. Now for this particular G here, right, if you take some element here and we have the mapping defined from C star to C star like this. Now if you take some element present here in the range, so it would map to exactly 4 elements in the domain, correct? So 4 elements in the domain. So this is a 4 to 1 mapping. How we are sure it is a 4 to 1 mapping? Because we have a property relating to that. This property tell you that if the kernel phi contains n number of elements within it, then this mapping would be a n to 1 mapping. Right now, because the kernel contains 4 elements within it, hence it is a 4 to 1 mapping, correct? Okay. Now let's see, take another question. Let's see which all elements in C star map to phi, under phi to 2. So that means we are looking for all those elements whose we are looking for all the pre-images of the element 2. Now you know it is a 4 to 1 mapping, so it would map to exactly 4 elements here, correct? So we have to see what is phi inverse 2, correct? So you can clearly see when you take 2 raised to power 1 by 4, so 2 raised to power 1 by 4 whole raised to power 4 is 2. Therefore it is one of the member. Therefore, you know, the this coset kernel phi together with this element taken from C star, this is what? This is the consisting of all the elements which map to 2. Why? Because we have this result that whenever phi of G is equal to G dash, then phi inverse G dash would be this coset G kernel phi, and we define it like this, correct? So which all elements would it contain? So in order to calculate this kernel, you have to multiply 1 by 4 with all the elements of the kernel, right? So you have to multiply 2 raised to power 1 by 4 with each one of it, correct? So once you do that, you have this as your set. Hence this is the list of all the members which, when taking power 4, that means whenever we take phi of it, would give you the answer as 2. Correct? Okay. Now next, we consider H to be some subgroup which is a cyclic subgroup of our group G, right, C star, and such that it is generated by cis 30 degree. Now what is cis 30 degree? It is cos 30 degree plus iota sin 30 degree. That you might know from the linear algebra course. Okay. So here we are saying our subgroup H is cyclic in nature and it is generated by cis 30. Now we have to see what is the order of the subgroup. Now we can make use of the de Moivre's theorem here. By the de Moivre's theorem, we have cos theta plus iota sin theta. So basically cis theta raised to power n. You might be familiar with this notation that cis theta is what? It is cos theta plus iota sin theta. So cis theta whole raised to power n is equals to cis of n theta. This is the result. This is the de Moivre's theorem, right? So here we'll make use of this result in order to calculate the powers of cis theta 30 degree, because we wanted to see how many elements are present here. So we have to take the powers of this cis 30 degree, right? So when you take different powers, raised to power 1 is cis 30, raised to power 2 is cis 60, raised to power 3 is 90. By using this result, we are able to compute all the values. So you see we have all the angles multiple of 30. Cis 30 degrees is 60, 690, 120, 150, 180, 210, 240, 270, 300 and 330 and 360, right? Because if you go to the power 13, right, then in that case you would have cis 30 degree raised to power 13, which is cis of 13 into 30 degrees. So it would be cis of actually 360 plus 30. So it would give you the answer as cis 30 only, which we have already calculated here above, right? So the cycle would be repeated by itself. Hence we only have 12 elements present within the subgroup H. Hence the order of H is 12. As simple as that. Correct? Moreover, we know if this subgroup is cyclic, then the image, homomorphic image of that subgroup is also cyclic in nature, right? So that means when you apply phi onto H, you would have some image which is also cyclic. So it would also be generated by some particular element. So we would say phi of H is equal to H raised to power 4, which is cis 30 raised to power 4, right? What is it? It is 6 of 120 degree, correct? So what is the order of this phi of H? Let's see. If you take cis raised to power 120 raised to power 1, it is cis 120. Cis 120 raised to power 2 is cis 240. Cis 120 raised to power 3 is cis 360. Correct? So the order here is 3. So from here we can make this observation that the order of phi of H divides the order of H. The order of phi of H is 3. The order of H was 12, right? So therefore 3 divides 12, hence here we have verified this result that whenever the order of H is n, then the order of phi of H divides n. Well, I hope you understood this example well. Well, that is it for this video. Thank you for watching.